The mass spectrometer. Here we have a simplified diagram of a mass spectrometer. Starting here, this will be the source of the sample, which would send neutral gas particles into this region, which is called the ionization chamber. Up here we have a heated cathode. The filament here heats up, and by thermionic emission there will be a cloud of electrons around here. Down here we have a positive electron trap. So in effect here we have an electron gun arrangement, and that produces a beam of electrons. These electrons will collide with the neutral gas particles, knocking electrons off them and producing positive ions in this region. Here we have an accelerating cathode, negatively charged, so the positive ions will accelerate towards the cathode, some passing through the hole in the middle. The positive ions then pass through this velocity selector. This is covered in more detail in a moment. They can then pass through this tube. The shaded green region is representing a magnetic field going into the screen. And finally, certain particles will arrive at the detector. As the name suggests, only particles with a particular velocity will pass through the velocity selector here, coming out of this gap on the right. The magnetic field then will cause the positive ions to curve round in this direction. You can verify that using Fleming's left-hand rule, pointing your first finger of your left hand towards the screen. They are positive ions, so the current moves in the same direction as the ions, towards the right and up, and your thumb for the thrust should now be pointing towards the centre of the radius of this circular path. Ions that have the mass that has been selected by the settings of the magnetic field strength will follow a path like this and be detected. Ions with the same charge that are slightly heavier will not be bent quite so much and may follow a path like this, hitting the side of the tube. So this is the fate of particles with a larger mass. Particles with a lower mass will be deflected more by the magnetic field and follow a path something like this. So that is the fate of particles with a smaller mass. So only the particles with the particular mass selected by the strength of the magnetic field will be detected here. The magnetic field strength can be changed to find the number of particles with different masses. Let's just look at the velocity selector in a bit more detail. The green shaded region represents the magnetic field going into the screen. Here we have a positively charged metal plate, and here a negatively charged metal plate. This produces an electric field of field strength E between the plates. The positively charged ions enter through this slit on the left-hand side and pass in this direction. When we have an ion at this position, it will experience a force downwards due to its charge and the electric field strength, the force being given by EQ. Due to its movement in the magnetic field, it will also experience a force up, given by the magnetic flux density B, multiplied by the charge on the ion Q, multiplied by its velocity V. If this ion is to leave the velocity selector through this right-hand slit, it must follow a straight line, and therefore the two forces, the force up BQV and the force down EQ, must balance. We can rearrange this to find that the velocity of the ion V is equal to the electric field strength divided by the magnetic flux density. So we can adjust the electric field strength and the magnetic field to select ions with the particular velocity we want.